Wang from a computer science department. And this is my great honor and pleasure to introduce our future colleague, Dr. Bryan Donyanavard, and he prefers us to call him Donny. So please let me introduce Donny. And he is a researcher currently in the IoT and Cyber Physical System group at Ericsson Research in Stockholm, Sweden. And he will join us in computer science faculty in January 2021. His research focuses on runtime management of resource-constrained computing systems. He received his PhD in computer science from UC Irvine in 2019. He has previously worked as a software engineer at Sun Microsystems and Google, and he spent time as a visiting researcher in Technical University of Munich in Germany. His research talk today is the intelligent management of systems through computational self-awareness. All right, please welcome Donny.
Thanks, Professor Wang. I appreciate it. And thanks for hosting me, guys, and giving me the opportunity to share my work a little bit ahead. And again, Bryan or Donny is fine. No need for more than I'd ask anybody. A bit of a mouthful. I'm here today to talk about work I've done in the past, and then at the end, hopefully spend a few minutes on the work that I'm doing now currently at Ericsson Research that I'm planning to continue for the foreseeable future. SDSU in the computer science department, and that's related to so I added another self here, which is a bit redundant, but hopefully the meaning of this is from very wordy the end of the so I don't know how you guys usually do this, but if you want to interrupt discussion throughout or wait to the end, but here is with first a disclaimer about the fact that I'm not or neuromorphic computing. It's not intelligent machine or systems, at least in the. It's more about enabling systems in an intelligent manner, which maybe makes them intelligent in turn, but not talking about understanding how the brain works.
Hey Donny, can I interrupt you real quick? This is Bill Bartling. So in Zoom, to preserve bandwidth, sometimes it helps if you turn off your video feed to us. Your audio is breaking up, and then I certainly personally want to hear every word you say. So. Keep your shared screen on. Just turn off your personal video feed. And that'll preserve your bandwidth, and we'll see your slides and hear you.
Okay, let me know if it continues to be an issue. Sorry about that.
Already better. Fantastic.
Okay, awesome. All right, great. Okay, still. All right, I'll assume we're all good. To get everybody's mind in the right place, we're not talking about the science of the brain or anything related to that. Out here is more of a psychological. I like this scientists. It's very vague and not so scientific, but self-awareness in humans is essentially the capacity the object of one's own attention, right? So being aware of who you are and what your purpose is. For example, in this case, you have a football each soccer player on a team knows that they're part of a team and knows that what their role with and their goals in a very explicit manner, right? Like if my job is to stop the ball from passing me, or if I'm so it's such a non-scientific definition here, but what we're going to do is we're going to leverage this for inspiration in the way that we approach, in my case, resource managers. Key concept that I'm going to this is, well, just again, a person trying to iron a shirt and not being able to deduce that the temperature in the iron is hot enough to burn their hand without actually burning your hand first, right? Through updating your decision making from that point on, right? Reflection would be the ability, or a reflective person would be someone that has the ability to perform ironing the t-shirt without ironing over your hand to figure out maybe I should move it, and this is probably hot enough to really do some damage. I think that we're all in the latter category here in the reflective mode. So what and strategizing ahead of time, inferring of your environment and so on. And so this is why. So let's move a bit the computing domain just one step further by looking at self-awareness in computing, and the literal textbook example of this from the ability to capture model about itself, capture knowledge about itself and model its environment on an ongoing, right? So you can see here with the example of self-awareness, for example, our software had his goal, and he can make very minute decisions towards achieving that with being able to sense his environment, right? So we want to be able to enable computers to do the same thing, right? And this isn't such a new concept, right? I think there's many people here who are scientific domains with these concepts. However, what this computational self-awareness umbrella, that is attempt to cover all of these disparate efforts in different research domains, common cause, so that we have people, in control theory and in AI, outside of computing and in math and modeling, that can leverage each other's work and really become aware and categorize themselves within this umbrella. So the overall theme here is that we want a computing system that uses self-models to make action decisions to achieve the goal. So what does one of these systems actually look like in practice? So we start out with a system without any awareness, right? But we need the potential to do those things we mentioned earlier, like sense the environment, and then also act on itself to reconfigure itself in some manner, right? So we can build on just a system with simply potential to make it reactive. And so here you have a more classic feedback loop that just allows sensing, evaluation of the current state of my system and its environment potentially. And then I can take actions based on how well I'm achieving some provided goal, right? But on top of this, to enable this to become self-aware, we want to make it reflective, right? So we go back to that concept of reflection, and we add the self-awareness engine on top here that adds a couple more loops here that now things are getting a bit more interesting, and it makes our reasoning engine a bit more powerful by giving it an idea of maybe the the environment, as well as kind of the ability to consider actions before actually carrying them out, for example, right? So this small addition of just the 2 more loops in this case, it is what really enables this intelligent management and self-awareness. So the core principles, again, reflection, and then really using that reflection to the overall goal, and the overall goal is to perform. Now, what's the context in which we want to apply this? So a combination of trends for specifically mobile resource devices. So if you think battery powered devices, right? So the first is we have increasing heterogeneity within each of these devices, right? They have a broad of efficiency and performance, and a lot of different types of resources that they can utilize. And we also have increasingly diverse and high performance applications and workloads, which are combinations of applications that we expect to execute in heterogeneous battery powered. Designers accounted for this wide range by both at design and runtime. You have the platforms have configurable parameters throughout the system stack at many layers. And these are all ways that we can balance this trade-off or explore this trade-off of efficiency and performance. So you have things like injection. So this is like very, very fine-grained management. And you have more coarse, like architecturally differentiated cores on the same chip, or powering off whole cores, right? And these things, this gets complicated because all of these different configurable parameters, they interact with each other, right? So these are dependent. So not only do we have a huge configuration space just considering each combination of all of these knobs, right? We have the complexity of the dynamic opportunity to trade off in this giant spectrum in a number of different ways, but it's extremely challenging. For example, at runtime, making sure I decision making that I'm requiring to make the decision itself. So what I'm going to hopefully convince you is that we need smart management, and a good way to do this is by looking at this concept to provide that smart management, right? So we're going to apply those principles to computer systems in the mobile and embedded world, right? So before we look at a couple case studies about using different principles of self-awareness, I'm just going to leave out closed loop resource management so that we're all kind of on the same page. So here, the feedback loop here, and this is the way that we're going to represent resource managers symbolically and conceptually, right? So you have the sense, reason, 3-step process here, right? And I've specified this in a way that I will also consistently define these resource management problems or instances, we can say, of resource management with specifying the goal, the sense data, the reason, what reasoning do I perform, what actions do I take. And in this case, this example is actually the Linux on-demand adding dynamic voltage and frequency at runtime. So this is, I mean, this ships with Linux and is one of the many DVFS governors that are available. And so it's extremely simple. Just as an example, you have a goal of keeping your core utilization below a specified threshold. You sense what is my current core utilization. I ask myself, is it above or below the threshold or at the threshold? And I increase, decrease, or maintain frequency on what the outcome of that comparison is, right? So this is kind of this reactive feedback loop for traditional closed loop resource. What we want to perform this same type of tasks right here. However, we're going to adding appropriate degrees of self-awareness, right? More complex is not always better. I think that simple solution is often effective. But the idea is that we're going to carefully design in different manners of reflection on a case-by-case basis to improve this management. And some area in different parts of this new loops that I won't have time to go over today are here. So looking at memory phasic behavior, which is really getting an idea of how is the then making your management decision, right? So improving your reasoning by understanding really how have your inputs changed. Also doing predictive modeling to improve your decisions to make them more effective because you have a more accurate model to evaluate, as well as gain scaling, which I can ignore because I actually am going to talk about that. So if that's not familiar, I'll get to that in a bit. Through a couple of use cases here. First of which is going to be about a property called self-adaptivity. And I'll explain what that means. Don't worry, I do not expect you to be familiar. So let's go back to a human example, self-adaptivity. So at a high level, what handling change due to external stimuli, right? So uncontrollable things like maybe a change in input or things in your environment change unexpectedly, and then what your goal is or how you achieve it, right? So let's think about this case here where I'm bowling, exactly the scenario with my 2 pins in this out manner, right? Now, I don't bowl, so every bowling shot is difficult for me, but this one strikes me as particularly difficult. And you can imagine there's a couple approaches you could have here if you were trying to knock the pin matter. You could either maybe safer, or maybe you could take a riskier shot that has a higher potential reward but a higher chance of failure to go for both pins, right? And how do you make that decision? Well, maybe it matters who you're playing and what the current the score, for example. So if I really hate losing to my sister at anything, so if I'm playing my sister and I am losing, then right, I either you win by 1 or 2. If I'm beating her, I'd probably play it a bit safer to try to protect. The key here is what we want to do is make sure our scenario, our context changes. We want to constrain our behavior so that in this case, bumpers. Self-adaptivity is the property allows us to adapt to changing goals due to the external stimuli. So let's manifest within a computing system. And here's a system that we're going to explore in our use case to give you an idea. So you have a multi-core heterogeneous, this is actually a mobile that we are executing one or more applications that we categorize QoS or non-QoS. So this is quality of service applications. And what I mean by quality of service here is really that we care about, we have an expectation of performance for this application, right? So a QoS application, you can think of a typical mobile scenario in which your QoS application is whatever you're doing in the foreground, whether that's checking email or watching a video or playing a game. You're going to have certain expectations about the performance of that. Non-QoS applications are what we would consider background tasks, things that are going on that you're not interacting directly with, maybe that you don't mind their performance so much. We're not paying attention to how well they're performing, like, yeah, refreshing your email or compressing stuff or something like that. So now the resource management we want to address within this system is managing QoS within a power performance that I here is vague because quality of service is an application metric. So depending on your application, you may have a different metric to evaluate performance. Going to maintain a given provided QoS within a power budget. So that's to say we have a target value for performance and we have a maximum value for power that we always want to remain below, right? And within that power budget, we of course always want to operate as efficiently as possible, right? So our goal is maintain the target QoS and operate within the budget. Our data we're going to sense in this case is total power and total QoS. That makes sense, right? We need to know system power in order to honor the budget, and we need to know the application QoS to make sure we're achieving it. The reasoning is, are we within the power budget and are we achieving QoS? The order of this is actually important, right? The power budget, we're considering a constraint that's essentially expressing the safe state of execution for our system. So we always want to honor the power budget all the time. And then once we have made sure that that's being satisfied, that constraint, our best effort kind of secondary goal is to achieve QoS, right? So we're going to prioritize power when those two things are not both achievable. The actions then we're going to take to achieve this goal is to set the frequency, the operating frequency of the cores, and also how many of those cores are idle, right? So we're going to kind of this is a pseudo power saving state. It's kind of emulating power gating of the cores by forcing them to be idle, right? Okay. We're going to do in this case, our mechanism of awareness is a supervisor over classical feedback controllers, right? So we have a supervisory, we use supervisory control theory to design a supervisor on top of some standard feedback controllers. And what this provides two really important things. One is scalability, right? So and decompose our low-level controllers to more of them for more cores. Excuse me. And we can also simplify the low-level control problem by decomposing our system into multiple subsystems, right? And then we also support this self-adaptivity, right? So we added our nice self-awareness loop here that's going to monitor what is the context of my environment, make sure that I'm always prioritized. For example, do I need to be reducing power? Do I need to be improving? Is my QoS. We do that is we deploy this high-level supervisor and guides the low-level controllers. And in this case, we use simple single input, single output classical feedback controllers. And our management hierarchy that we described before, right? So you see we've added a middleware layer here. This is just the name of our resource manager that we've named, so that we've designed rather. So this consists of an entire middleware layer that contains the whole supervisory resource management middleware layer. It is actually designed in the way as disparate low-level controllers and then one separate supervisor controller module. And then there's additionally, you see a small component here in the Linux kernel, and this is in order to enable this sensing of the platform that we need to do, right? So for example, we have to sense power from the hardware, and we also have to sense QoS from the application. So we require some kernel modifications, or rather we designed an additional kernel module to enable the information sharing into the user level where we implement the actual controller. Okay, so how does this work out? Well, what we're looking at now is 2 time plots. On top, I have my QoS, which is frames per second. Is a video codec, X264. I'm for the same exact experiment, what is my power, right? So this is the total SoC power measured over time as well. And you can see the colored lines are the measured values, and the dotted line OS. And in the power case, it's going to be the budget, the maximum power here, right? So we have 3 phases of execution. The first is what we call the safe phase, where we have a single alone, where we can achieve the target QoS well within the power budget. Next phase is what we call the emergency phase, in which you can see we've changed significantly lower than it was originally with the same application executing. And you can see that there's a bit of exploration. So there's a period where you can see our system state is changing. Able to settle on actually a QoS right at the edge of the power budget. Success. Final phase we call the disturbance phase. We revert our power budget and the target to the same as the first phase, except now we execute background tasks. So we add a bunch of non-QoS tasks in the background, and it turns out that this makes it so that we cannot achieve our QoS any longer within the power budget. So what you can see phase 3, our power starts ramping up as our measured QoS decreases in order to try to account for this decrease in QoS, and we're able to make a slight difference, but then eventually we're throttled because we meet the power budget and make sure that we never exceed that, right? So in general, we're able to successfully meet the FPS target when it's possible, and we always honor the power budget. So this is just a successful automatic prioritization of a multi-objective goal. That's the overall achievement here. Okay. Now moving to another property, computational self-awareness that we're going to explore, self-optimization. I'm going to look at 2 briefly of this this concept. Okay, but first, to understand what exactly is self-optimization and what I mean when I say that. So before we talked about self-adaptivity, and it was about adapting our goal to some changing external uncontrollable stimuli. Self-optimization is more about internal dynamics, really things that are captured within our model. So in the case of bowling, you can see now we have a much simpler scenario, right? I'm bowling, there's 1 pin up, my goal is very straightforward, knock that pin down, right? So of course I'm going to bowl my ball in order to do that. However, it's totally possible, of course, that I miss due to a number of different reasons, not bad at bowling, right? Is smoother than it is in reality, or it's uneven, or the ball is heavier than I thought. So essentially, these are all things that are within the system and the mechanism, the action mechanism, account for accurately enough, right? So I have unpredictability internally, and my poor assumptions or model has caused my act correct, right? So the question we want to answer here, or the property we want to provide, is improving efficiency, efficacy of variation that is internal to our system, right? So how are we going to apply this to resource management? Super simple system. Just think about the scaling policy or a DVFS governor for a single core chip. A goal is going to be is maintain some target power value. So in the previous case, we talked about having a power budget, right? But in this case, target specific value we want to achieve, right? So this is a very straightforward problem for classical control. The data we're going to sense is appropriately, right? We either up, down, or we don't move. So super straightforward. However, it turns like use a linear controller to do this. The relationship in some cores to frequency, power with respect to frequency, right? So what you see here is just a plotting of the measured power of an ARM core over its entire range of valid frequencies. So the DVFS, the programmable DVFS governor, allows you to set any of these frequency, and you can see that you could estimate a lot of this probably pretty accurately with a linear model. But once you get up here, you're going to run into some imperfections in your model. So what we do is we take a very straightforward concept, and we break this whole range down into operating regions. And this is extremely easy in this case, because it happens that although we have a very wide range of frequencies from 200 to 2000 megahertz, we actually only have 4 different voltages. So as a first pass, we split the frequency groups up operating by the identify linear models for these operating regions that are smaller and more accurate. So this simple decomposition. And it turns out that this works pretty good. Pretty good. I mean, what I say pretty good. What I mean is we get about 10%. We get about 10% in power for the same amount of work. Just take my classical controller that I designed 4 of them and add a layer of top of them that for no overhead in work, right? So in this case, reflection that considers what I'm operating in before deploying a controller. So what I do is I take my classic feedback controller, add what's called a gain scheduler, and before taking my action, I simply ask, what's my current operating frequency? And if it's outside of my previous operating frequency operating region, then I switch my controller to be the one optimized for my new region. So what happens is maybe you invoke your controller an extra iteration at one extra time in a relatively infrequent rate, right? So what happens is you end up getting more due to that more, you gain more accuracy due to the improved models, then you end up repeating work, right? So a single linear model. This is just a first pass, right? We added a very here that improved our reasoning engine, just a bit more accurate models, but it was a slightly arbitrary, right? I was just I had the same problem put it off a bit more by breaking down. I use the same linear modeling technique, the range of frequencies. It just is a first step. What we really want to do is we want to continuously update this model based on observation to make sure it's as accurate as possible. And this is really the ideal in self-optimization. And what we can do is we can use reinforcement learning to give that a shot. I'm going to switch here because if we can do, I'm going to switch target metrics from power to QoS error, right? Because there's a really powerful thing that continuous model updates enables, and that's to dynamically identify dynamic application or hardware specific, system specific, that we cannot do if we have a fixed model. So handle changing relationship between, say, frequency and QoS, right? We could do that in the previous case for the power, it worked out fine. But in this case for QoS, it actually wouldn't work at all. But even if we gave it a try, you can see here that the in the brown line, what you have is a reinforcement learner, just a straightforward Q learning agent. The pink line, you have our classical controller that uses the method that I just discussed for the y-axis, it's error. So this is how well are we achieving a target QoS? If I'm provided a target QoS, can I achieve it? And so this is essentially the same information we saw on the time plots for the self-adaptivity plot. I just wanted to make sure everyone's paying attention, pretty much. So initialized model has an error of almost 100% to start. But if we let it run for a while, classic controller. Remember, our classic controller has the best defined model on the exact work that we're trying to control. So it's kind of like cheating. I would say it's not a practical solution. And it really the gold standard. This is as good as we can really expect to do, right? So this is really promising to me. So we can now adapt to heterogeneity in the platform and the application as well, right? Which is something we couldn't do before. So what we did when seeing the promising behavior of the unoptimized Q learner, we designed a hardware module to provide reinforcement learning agent that then can perform this control for DVFS very efficiently and frequently, right? In the rate at which you would expect to change the frequency in hardware, right? So I'll just walk through the logic of it, and if you learning, this is essentially an XCS, a simplification of an XCS agent, which is kind of an extension of a classifier system. So it's like a bit of a pared down Q learning agent implemented in hardware. So, and this is just a table with a set of rules, right? Where we have conditions. So these are current state, action vector, and then what is the accumulated reward, essentially, or expected reward, we could say. So the first thing I do, I invoke my agent, is I check my population for the current state. Check my population for rules that match. So what are my sensor values and conditions that match that? Then that gives me my match set, which is some set of the population. And out of that match set, I need to pick one rule to apply its action to the system, right? So I use an action selection algorithm to select my action set. And then that gives me the action I'm going to take, and I carry it out on execute for a while. I observe, I measure normal execution, and then finally I read my sensors again to see how close was I to achieving my goal. So I really measure my objectives and then evaluate the objective function and calculate the reward. And then I use the reward to update my population again. And I start over. I iterate over and over, right? So what we did is we deployed this to control DVFS and compared it against our kind of ideal controller, which is the classic controller here. And so now we see two time plots again, back to the time plots. So this is execution of k-means, which is a simple data-driven application over time. And the y-axis in both cases is instructions per second, which is our performance metric, right? So you see a dotted line, which is our instructions per second, the blue line, which is the measured instructions per second, and then the orange here is the showing us how good are we doing at achieving what our target is. So the error, the better, right? Okay, so ignore the second half of execution because that's for actually a set. Look at the first half of execution here. We can see that there's a clear distinction in our reinforcement learning, which, by the way, that's where LCT comes from. So there's a clear exploration phase, right? But after a certain point, we disable exploration, right? And we do a pretty good job of target, and our error goes down consistently. And start with a relatively high error, but you approach towards the optimal, sorry, not optimal, the target. But in the end, they're ignore, of course, it's important, but if you exploration, it tells me that we're essentially able to identify the same model advantage of prior observation and this case, right? So LDT was I identify system dynamics from scratch, and then also able to adapt to changes, and we designed an LCT that then did power optimization as well. So in QoS power similarly to the self-adaptivity example, but that's all in this paper if you're interested about that as well. So the takeaway here, say simple applications and embedded systems. So even what you might call unintelligent means to varying degrees, right? As you saw, it was very useful to apply not only different management problem, but also the complexity of the solution itself is a component, important decision to make when deploying the resource management itself. High level, very abstract models and representations of not only the system, but also the goals. And then we typically deploy simpler low level controllers to actually carry high level goal management and low level control. And this has yielded some pretty good results for us, right? There are a lot of interesting questions that we tried to address a few interesting questions, but there are much more that apply to a wide variety of systems and applications that we can model in this same way, right? You can imagine this problem it manifests in many ways, in many different systems. So for example, the green here you see is today energy and safety. It's not something I talked about today, but recent work we've addressed. And I'm expanding these same principles, looking energy efficiency, QoS awareness, into mixed critical systems, as well as IoT networks. And IoT network, my current and I should say ongoing and future work related to Ericsson. But just before, acknowledge also the fact that these problems occur in the data center level as well, right? Even systems, there's still about the efficiency. And then we can also expand our concepts into safety, not only just safety, but security as well. So there's a lot of things, really cool things to look at in emerging applications and different system types. So speaking of emerging applications and different system types, so with Ericsson is problems, right? So doing the making for configurable applications in the context of localization and mapping over 5G networks, right? So what we're trying to do here is we have a goal and we have constraints, of course, and then we want to algorithm and the platform and mapping application in order to be both high performance but efficient devices, right? So yeah, the one of the huge benefits of the low latencies of 5G is going to be the ability, again, to do edge offloading from very low power efficient devices for a lot of data. But we need to know exactly how much offloading should we do to the edge, when should we do it. Cool problems that I'm looking at with respect to this kind of optimization when you have variable network service, right? So your network happens when you have multiple QoS apps focused on a single QoS application, but that's not the reality of cyber physical systems that we're going to use to interact with the environment increasingly in the future. And of course, everything is battery powered. These are just references of all the work that I talked about or referred to in this presentation, and of course, people than just me. And I, as of this week, have officially an SDSU contact. So feel free to contact me for about anything in the future. So I'm if you're interested in knowing more about past work or ongoing work or working on these topics, then please reach out. That's it.
Can I ask a question?
Yeah, sorry, questions, go for it. Yep.
Hey, Donny, very nice work. So first off, question. So do you assume the continuous frequency, or you only assume the, discrete?
Discrete, yeah, it's discrete. Exactly how the work in Linux, essentially. So if you want to know specifics, these are actually all of the discrete values you see here. So it's every 100 megahertz from 200 to 2000. If you want to look, for example, at the Odroid, that's
okay. Now, the other question is, do you assume that the application has the same, or you generalize the quality of service into, a fixed criteria? or you have multiple applications which does have different quality of service requirements?
So that's a really important one. As you could see, even from this presentation, I talked about 2 different qualities of service application, and in this application, it's instructions per second, which is just general throughput. This is a really good question, and for me now, quality of service, I'm trying to target as a domain specific rather than application specific. I mean, maybe you can consider those the same thing, but for example, what we can do when we look at localization and mapping is we can say the task of localization and mapping itself, we can define general metrics for quality of that domain, right?
Yes and no. Yes, you're right. We can assume they are the same, but then when you do the localization, some of the localization may need an urgent reply when it's getting to the close proximity, or if you see what I'm saying?
Yeah, sorry. Did you mean the requirement for quality of service or the metric? Maybe I could clarify better.
Yeah, the requirement of application.
Yes, sorry, I misunderstood. My mistake. I was talking about the metric itself. Yeah, the requirement is application specific, and that's part of the reason that we've moved towards the online is because not only do we expect the actual target of quality of service to change over time, but we even for a consistent quality of service target, the dynamics with respect to that of your environment, that exactly your speed can dictate what platform settings or algorithm settings can achieve an accuracy. If I want to talk about localization, for example, if I say I always want less than 5 centimeters of error in positioning my own, if your drone is going 60 miles an hour or 20 miles an hour, the algorithm settings, like for example, your input camera speed, required to achieve that 5 centimeters may change. So you have to be flexible. You have to have flexible models.
Okay,
Yep.
I have 2 more questions, but I want to give other people a chance, so I'll save it.
Anybody else, feel free to unmute yourself and ask questions. And thank you, Donnie, for a nice presentation.
If nobody else, then I have 2 more questions to ask. But
Sure.
okay, the other question I have is that we all know when you scale down the frequency, the reliability decreases. Do you consider that?
No, another great ability. I guess it depends on what you mean about reliability of the hardware system itself. Do you mean?
Yeah, because when I did a DVFS for ensure the deadlines, and we know if we scaled it too low to save power, then we have to consider the failure rate increases. That's what I'm saying.
Great point as well. And another thing you can see that is maybe glaringly absent to somebody as familiar with robustness, right? So I didn't talk about application errors because the applications that we've looked at we're not really considering any application errors. Yeah, great. Very ideal.
Okay, thanks.
Yeah, but it's definitely a topic for future.
Yeah, and then the last one is when you do the reinforcement learning, are you doing it online or offline?
Online at runtime in hardware.
I
Yep.
see. Okay, well.
Yeah, so that's what why you can see, and this is throughout execution. You can see you start with a huge error. because in this case we didn't initialize the model, but the population was designed, right? So the rules that I have are somehow targeted for this system and DVFS itself.
All right. Thank you so much. Thanks.
And we actually evaluated this on hardware as well. So we had a simulation environment in Gem 5, so architectural simulator, and we also had an implementation on an FPGA with on 3 multi-core. So we did this for a Spark, OpenSpark multi-core that we fabricated on FPGA. Synthesized, not fabricated, sorry. Synthesized. Yeah.
Okay, thanks.
Any other questions? Comments? Well, in that case, we thank you, Donny, for a very nice talk, and thank you everybody for attending, and have a nice weekend.
Yeah, thanks again for having me. If anybody wants to reach out, shouldn't be hard to find me.
Thanks, Donny.
Bye.
Thank you.